Welcome to Mechanics of Composite Materials. Today we'll be discussing design guidelines in dealing with composites. One of the things I want to talk about is the composite structural verification approaches. And it's a very top level, what I'm going to cover right now, but the point I want to make is analyzing a composite material or structure can be quite complex. And so, but we have to analyze the composite structure ahead of any manufacturing, even for qualification, because if I want to qualify a structure, I want to make sure I'm successful at qualifying a structure. So you definitely want to still develop the analysis capabilities to ensure success during the qualification program of that structure. The qualification of the structure is important because it verifies the manufacturing processes. It basically certifies the personnel, the training, everything that went into making that composite. It helps you gain confidence that the processes were robust. The fabrication of the production unit after that one can be verified in many different ways. You have the process controls, making sure you have a fault prevention plan, basically ensuring that you don't get contaminants within the composite as you make it, making sure you keep the shop clean, keeping the procedures up to date, making sure your build paperwork is robust, all the things that will come into making a composite is what you want to make sure that those processes are robust. A non-destructive evaluation further can increase confidence in the manufacturing of the composite by revealing any flaws that could have been that could form during the manufacturing process, or perhaps somebody left a backing paper, or there's a paint chip that came in there, or there's contaminants like grease. The purpose of the non-destructive evaluation is to find those areas of concern. And so the analysis, the way analysis can be helpful, and it can be combined with testing, is that it can help you define the threshold of what kinds of flaws are acceptable. You can imagine that, you know, you may have flaws that could be 1 inch, 2 inches, but it will be very painful if we reject the whole hardware. May as well come up with acceptance criteria that you can use to apply to the hardware, where you could either accept the flaw that you have, or if you need to reject, it can trigger repair. We'll be talking about repairs, you know, in the future. There'll be a YouTube video where you can check out repairs. But what I want to talk about here is, what are we trying to achieve? We're trying to achieve a composite structure that is robust over the lifetime of the program. One of the things you want to make sure is that the unit you produced is robust. And one way to do that is through an acceptance test. An acceptance test can be through a proof test. The proof test, what it does, it could apply a load higher than the operational loads, and usually it's adjusted for the environmental correction factor. So say that in flight, you may see 200 degrees F. We know the strength of the composite is decreased at 200 F, but the testing you perform on the ground is at room temperature. You can correct the proof factor and increase it over the operational loads to be able to account for the test like in flight differences. And the purpose of this proof test is to show that there's no workmanship issues that could be of grave concern. Non-destructive inspection after the proof test even further increases confidence, because before the proof test, if there was a weak bond, that weak bond will open up during the proof testing, and perhaps you can capture it after the proof test. And there's an issue, you can then correct it through a repair. And so, so these are the basic good practices for the design, qualification, and workmanship verification of a composite structure. However, keep in mind that different approaches exist in the aircraft industry, in the spacecraft industry, in the launch vehicle industry, and then in the sporting goods industry or consumer applications. So it's very important to understand that every program is going to have unique requirements, but that in general, ingredients such as this could be very beneficial, such as non-destructive evaluation, qualification testing, verifying that you have good workmanship, and then even performing a proof test to check that your structure is robust for the one that you actually manufactured for use in service. Over the years, we have learned that composites can be structurally efficient, but that we need to apply sound engineering judgment, and that we need to figure out guidelines that can help us, design robust composite structures. To that end, engineers over time have come up with lessons learned and best practices that are believed to minimize design and manufacturing risks with composite structures. And so what I want to do is to talk about some of those lessons learned that I think could be useful. And we'll be talking about that in today's lecture. But for example, I first want to talk about the issues with composite structures. One of the things that you see is that composite structures, unlike metals, will have a low interlaminar tension strength in general. A low interlaminar tension strength of about, say, 3,000 psi to 8,000 psi, fairly low. And so if you have load eccentricities and out of plane loads, it could lead to some delaminations. This can also happen when you have many stacking sequences that have too many plies at a given angle. And so that can cause residual stresses that can decrease the effective interlaminar strength capability. And so we also know that there are some nonlinear rate-dependent responses for many polymer resins. Laminates carry significant amount of the load, and the resin matrix dominated directions may creep. That's particularly a potential issue for elevated temperatures. You could then start exhibiting, these composites could start exhibiting a nonlinear stress strain response as well. So the operational environments can induce creep. So it's important to keep that in mind as you're designing a composite, and not lose sight of these particular issues. Microcracking of a polymer matrix is something that could happen. Resin matrix cracks may not always immediately structurally degrade the structural properties, but their propagation can lead to pressure cabin or fuel tank leads, as well as degradation in the durability and damage tolerance. So such cracks can allow the ingression of moisture and other fluids. And if you were to have cyclic freezing and thawing of these liquids occurring, crack propagation can be accelerated in these circumstances. So it's very important to consider that while microcracking can be beneficial in some cases, it can be detrimental in other situations. The order of magnitude differences in the coefficient of thermal expansion can be quite problematic. One of the issues that you have is that if you have a composite that has if you're attaching the composites to a metal, for example, the composites will have a lower coefficient of thermal expansion compared to the metal, for example. And if these two things are bonded together, the coefficient of thermal expansion can be such that the materials could deform at different rates, and as a consequence, it could cause a potential catastrophic failure of the bond line. Another consideration to keep in mind is that when you're manufacturing composites, depending upon the stacking sequence, but you may find that since there's a mismatch in the CTE, in the parallel and transverse to the fiber directions, that you can now introduce unacceptable warping and thermal stresses, especially if you use non-symmetric lips, and if you're using these kind of applications in spacecraft, which are supporting a mirror or something like that. that's where this could be a potential concern. And so it is important to understand that the CTE can be a problematic point from various standpoints. Another thing I want to discuss right now is out-of-plane loads. These are examples of out-of-plane loads that you could have in application. And for example, here you have a configuration which is a flat-wise tension configuration where the stiffener is pulled away from the base structure. And an explanation of that, or an example of that, would be a skin stiffener separation due to normal pressure loading conditions. An application of that is going to be a windskin or spar flat-wise tension due to internal field pressure. That's an example where you could see that. A transverse tension situation is one where you're applying loading in the base, and that since the stiffener is not taking much load, that it could cause edge stresses. A stiffener web splitting due to transverse tension loading is what you're seeing there. An example of that will be a windskin spar transverse tension due to chord-wise loads. You could also have a situation of lateral bending where the skin stiffener separation due to lateral stiffener bending could occur. An example of that will be a lateral spar bending due to asymmetric field pressure. So these are just examples of where you could see it, and this is a description of the load we're talking about. And in all these cases, the concern is that the out-of-plane loads can cause these delaminations between the composite layer, within the composite layer. Post-buckling is another situation you could have. It could be due to a combination of compression loading. Even lateral loads can cause buckling. And so stiffened panels subject to compression loading is an example where you could see this. Other situations where you could see out-of-plane loads are curved panel bending. So if you have a curved panel and you have bending on that, you could have a situation where out-of-plane loads could occur, which could lead to delaminations. Fuselage skins and frames subject to the bending loads is an example. Thickness which have transition regions where plies are dropping off, and what I mean with that is that a ply will not continue compared to other plies. And that can be done to build up the composite to a thicker section. Interlaminar stresses due to this eccentricity in the load path can cause delaminations right at the edges of this buildup. So ply drop-offs, buildups, and doublers are situations where you may see this. Irregular loading is another example where you could have interlaminar stresses and stresses that could be detrimental, that could cause delamination. And that could be situations where there's a presence of eccentricity, and that can happen if your design happens to have a joggle or a kink. Bonded joints, which by the way, I do have a YouTube video on bonded joints, and I know I didn't cover it in this course, but you may see it in one of my YouTube videos. I go into bonded joints. I invite you to take a view of that. But in general, interlaminar stresses would be quite high in these situations, and they will arise from the eccentricity in the load, but also due to the mismatch in the different materials modulus. This kind of situation will be encountered in lap joint situations. So continue with the issues with composite structures. You know, there is this concern of reducing the strength due to impact-induced damage. And the issue with composite structures is often that this damage may not, you may not see this damage because usually the surfaces tend to be dark, and it may not be visible. You can impact the surface, but then beneath you could have extensive damage. It's possible. And so this non-visible form of damage is a primary concern in all phases of certification of composite structures, for durability and damage tolerance in aircraft, launch vehicles, spacecraft. And so you gotta use some sort of damage indicator, and that can be paint, cork, or even protective devices to ensure that we don't introduce damage during the processing of the hardware, that you have insights into the hardware, that you're not missing something during the processing that can expose the structure to various levels of impact damage that could be detriment to the strength of the structure when it's actually put in service. We also have a situation of the reduced thermal conductivity relative to metals. The reduced thermal conductivity can result in the presence of higher thermal gradients than those that can occur in higher conductive metal structures. These gradients can cause unacceptable responses in the structure. For example, lightning damage can be more detrimental to composite because it's a more local type phenomena, that it will damage the composite since the heating was not able to get dissipated through the conductivity of the material. So the heat transfer is not very effective in these materials. We also have the situation where there's the environmental sensitivity of polymer resins. We know that there's a significant strength reduction of resin matrix influence properties, such as compressions and shear strength, and we covered some of that before, that can arise when the composite structure is subject to elevated temperatures and moisture. Not only moisture can be absorbed and cause dimensional instability, thermal can do that, but not only that, these two effects can also reduce the strength of the composite, and it is usually a limiting factor for high performance applications, like in the aerospace industry. We also have the situation of galvanic incompatibility between the graphite fibers and some metals. And so to prevent corrosion damage, guidelines as the ones required for titanium fasteners have been established. You want to put, perhaps layers of glass instead of graphite composite need to be interposed between graphite plies and aluminum surfaces to prevent this galvanic incompatibility. This is mostly efficiently accomplished by procuring the glass composite ply as the outer ply of the laminate. So I want you to pay attention, because galvanic galvanic corrosion can be a significant issue that if we don't pay attention to, it can be of significant concern. Reduce electrical conductivity relative to metals. The lessened electrical conductivity of composites can influence the response to lightning strike. I already talked about from the heat perspective, but at lightning strike attachment points to the exterior of the vehicle, damage may range from a superficial burn mark to some penetration into the skin. And so I already talked about the overheating issues, but charge built up within the fasteners is not carried away by the low conductivity of the composite, and instead you could have some ignite some vapors that could become flammable, or it could ignite in a fuel tank. Composite structures provide less electromagnetic shielding of interior electrical components, and so these components can be seriously damaged by static discharge. One technique used to mitigate these effects of lightning strike is to use a metallic mesh, like a copper mesh, to increase the conductivity and then at least shield some of these issues. And so we don't have an issue without, you may have some weight penalty, but at least you can tackle the lightning concerns. So another thing I want to talk about is design guidelines that should be thought of. So, one idea is to use symmetric laminates. It's not always easy to use symmetric laminates, depending upon the application. That might not be the best choice. But using symmetric laminates, and we talked about what symmetric laminates means, it just means that the plies in the stacking sequence mirror the midpoint or the midplane of the composite. Um, and so you may not be able to always enforce symmetric laminates at tapered zones, unfortunately. However, any asymmetric existing due to manufacturing constraints should be minimized because that's going to cause some amount of interlaminar stresses at times, and it could sometimes cause additional warping, twisting effects. It could introduce bending and maybe even coupling between extensional loading and bending stiffness. So the stiffer the laminate and the greater the asymmetries, the more preload or shimming may be required to provide an adequate fit up during manufacturing. This can result in significant stresses being induced in the part during assembly that may degrade the part's structural integrity. And so the benefits of using symmetric laminate is that you're able to prevent warping under thermal conditions and also uncouple the bending and membrane responses. We talked about some of this before, just trying to bring that to light again. Another thing I want to point out is there is this tendency of wanting to extrapolate test data when it comes to composites, but sometimes the testing is going to show that the strength or the modulus may not correlate linearly with temperature or moisture. And so you want to be careful because there could be a cliff. And so it's important that you always determine all the relevant properties relative to the design of a composite, and that you try not to be too quick at extrapolating test data. I think interpolating could be okay in many cases, but it is important to perform an adequate number of tests at the critical operating ranges. And so that is a major consideration that should be accounted for. You also want to keep a reasonable number of primary load carrying plies away from the outer surfaces. One of the reasons that's beneficial to do is because these critical plies are not easily damaged by minor impacts. The outer plies can then protect the inner plies, the ones that carry the most load, a little more carefully. So cloth plies, you're going to see very often is used in the outer surfaces because it will resist the matrix cracking events, and so you will have less splintering. The damage usually remains confined when you use cloth plies, so that's kind of nice, and it's easy to repair. However, that doesn't mean you're going to have, it's possible you're going to have subsurface damage. And so when you encounter that, it's important to perform some amount of non-destructive evaluation to find these potential damages that are hidden from the impact events. But the outer surfaces keep the plies are carrying the most of the load in the inside within the composite, and then the outer plies are more there to protect you. Now, one of the things I want to mention there is that you can use the idea of sacrificial plies. So say you have 20 plies that you need for composite, perhaps design to 26, and then keep the extra weight penalty mostly to protect yourself from potential for impact damage. So you have to kind of balance what do you want to do. If you want to keep it to 20 plies and you don't want to have any pocket margin, then perhaps you have to up your game when it comes to implementing the impact damage protection plan. Basically, what are you going to do to keep the composite from getting damaged? What are you going to do to find damage when it happens? Maybe you're using paint indicators or something, some sensitive paint that will tell you, hey, if something happened here, I better pay attention. And so laminates, they're symmetric and balanced, increase the buckling strength. So the presence of coupling between the bending and extension in a laminate generally increases deflections. That's the situation, that when you don't use a symmetric and balanced laminates, you're going to get the B matrix that couples the bending and extension stiffnesses, and we know that could increase deflections. So those will make it more prone to buckling. And so At the same time, it's important to understand that this coupling that could occur reduces buckling loads and vibration frequency significantly. Similarly, for laminates with twist curvature coupling, the deflections are increased, the buckling loads are decreased, and the vibration frequencies decrease as well. So very important to understand that the buckling loads and vibration frequencies get impacted when you don't use a symmetric laminate and when it's not balanced. Another thing that has been discussed extensively in the literature, and I invite you to pause the video and look for some research in this arena, but there is some understanding that adding plus minus 45-degree plies on the outer surfaces can increase stability of critical laminates. And so it is something to consider. Experimental observations indicate that the value of M, which is the M that goes into the buckling equation, this is an integer. So M is an integer. If you recall, we talked about the Navier solution using energy methods. And we solved some buckling problems with the Navier solution. And M was a parameter in the approximation, in the sine series. And so M typically yields a minimum value of the critical load such that M over A approximately equals 1 over B. Hence, the buckling load is a function of 4 times D66, which is a value within the D matrix, while only a function of 1 times D11 and D22. So these are like more going to the mathematical details. The point I want to say here is that when you add this plus minus 45 degrees, it affects the D matrix in a good way. It increases D66 and it's 4 times more effective in raising the buckling load than adding 0-90-degree plies. So there are examples in the literature that go through that, and there's plenty of plots that kind of demonstrate that. And here I have an example of gamma being plotted against these parameters and delta, and then gamma and delta are shown here, and the buckling coefficient generally increases when we can get those plus minus 45-degree plies in the outer surfaces. That will increase the stability of the structures fairly well. Using another thing I have not pointed out here is that using a larger fraction of plus minus plies in the shear dominated regions is a good idea, because shear loads are best handled with plus minus plies in a structure. We talked about that, plus minus 45 degrees. When we worked on optimization, I showed you how the plus minus 45 degrees will come up anytime we needed some shear being applied. Significant CTE mismatches among the bonded or core cured structures must be avoided. As we said, laminate CTEs, coefficient of thermal expansions, are a strong function of the layup due to the differences in CTE in the fiber direction versus the transverse direction. Significant residual stresses can build up during the cool down phase from the cure temperature down to room temperature. And then you could have the situations where excessive values of CTE can be avoided. And you can do that by using fiber-dominated laminates. So you can control the CTE behavior, and you can also even tailor it to get it closer to the metal if that's what you're bonding it to. That way, if you're bonding metal to composite, reducing the CTE mismatch can be useful for the bonded joint design. It's also very important to understand that resin matrix toughness it can be sufficient to prevent intralaminar cracks during cool down. So getting a good resin matrix system can go a long ways in your design. I also want to talk about a plus minus 45 ply that are in contact with each other is a good idea. It minimizes the interlaminar shear value. It's not what I'm covering here, but just throwing another good design practice. Operating temperatures of the laminate should be at least 50 degrees Fahrenheit below the wet glass transition temperature. That is a good idea. At elevated temperatures in the presence of moisture, the compression and shear properties of the resin matrix can degrade seriously. So this degradation is due to the plasticizing effects of the resin matrix when it is exposed to hot, wet environments that reduce its ability to support the fibers and increase the likelihood of fiber microbuckling. So matrix softening can occur due to the effect of moisture on the glass transition temperature. It's very important to understand that with increased moisture, your TG is dropping. But in addition to that, the strength can also be impacted by the effects of moisture and heat. And so again, it's very important to try to keep the operating temperature of the composite with some margin against the wet glass transition temperature. Another thing I want to point out before I run into this particular one is it's important to minimize stress concentrations. Composites are essentially elastic to failure, so keeping some amount of stress concentrations away can be very good for you. And so I also recommend that when you're using 090 plus minus 45 degree laminates with, you should have a minimum of one layer in each direction. I think it's good to have 090 and plus minus 45 at the very least. 0 layers for longitudinal loads, 90 layers for transverse load, plus minus 45 will take your shear, and it will make it quasi-isotropic. Now, quasi-isotropic may not be your best solution because it's not optimized. And so I really encourage you to use the optimizer code to determine what is best. But starting with these ply angles is not a bad idea. It gives you some starting point of what needs to be done. You don't need an equal number of plies at 090, but having one of at least each can provide some stability to your composite structure. Maintaining a homogeneous stacking sequence by having several plies of the same orientation together can result in increased strength. Also, minimizing the fiber orientation angle between adjacent plies is a good idea because it will reduce the free edge effects. I'll be talking about that in a minute, and it will avoid the idea of microcracking, particularly when you're looking at cryogenic applications or where you have wide temperature excursions where the effects of interlaminar stresses can come into play. So minimizing the fiber orientation angle between adjacent plies is a great idea. So let's now dive into a new set of design guidelines. We have one idea is to limit the interlaminar stresses due to CTE and Poisson's effect. In essence, minimizing the fiber orientation angle between adjacent plies is what I just discussed. When tapering composites, you want to drop off the plies in a way that's not detrimental, and that means maintaining up to 10 to 15 times the thickness of the ply when dropping the ply. What I mean there is, pretend you have a ply here. If I want to drop this ply, the thickness is T, so just drop it and then let it drop over a length of at least 10 to 15 times the thickness. And so limit the thickness of the laminate and number of contiguous plies of the same orientation. And so that's very important to consider. It will decrease the interlaminar stresses greatly, and you'll be in better shape. Here's an example of how laminates can impact depending upon the stacking sequence you select. So here's an example of the exact some number of plies. You can see here I have 4 ply symmetric in all these cases, and one of the things you can see here is that the one that gives me the least interlaminar, so this plot here is the interlaminar stresses through the thickness. And what you see here is the interlaminar stresses are the highest for stacking sequence 2 and 3. Okay, and that's 2 here and 3 here. And so those are resulting in huge stresses. But number 5 results in a much better situation. So again, you want to make sure that your design can reduce the amount of interlaminar stresses. If you can do that, you prevent potential for delaminations. So 2 and 3 have plus minus 45 degrees, and while plus minus 45 degrees can help you with a situation on the shear loads, depending upon how you stack it, it can lead you to vastly different results on the interlaminar stress predictions. So it's important to play around with your stacking sequence. One thing you can do is perform a highly, superly defined finite element analysis, not classical plate theory, but something more advanced than that, and look at the mesh and make sure you have good fine mesh density to study which stacking sequence may be the best for you. So again, very important consideration for composites. It's also very important to limit the stresses. You want to reduce the stresses between two materials because that can cause significant concerns. So limit the Poisson ratio mismatch between a stiffener and panel. That's exactly what you want to do. A design feature where that could happen, where the Poisson ratio can get involved, is a stiffener bonded to a core cured or core cured to a laminate. And so it's important that there might be good reasons for designing the stiffener with a fairly high percentage of 0 degrees along the x-axis, along this axis. The x-axis is this one, and that's to be able to reduce the Poisson ratio mismatch. There might be also good reasons for designing the skin laminates to be relatively rich in the plus minus 45. And so that way the Poisson contraction of the skin is resisted by the stiffener. And so then if you can reduce that mismatch, that'll suppress severe stresses between the skin and the stiffener. So basically bring the Poisson effects close to each other. One way you can test whether your structure has Poisson ratios that are similar is, for example, if I have the stiffener here and I apply a tension load, measure how much it contracts. Then take your laminate at the bottom, and here you can see that you want to apply a load and then see how much Poisson ratio you get in the other direction. And then just make sure the Poisson ratios on both ends are similar, and you can use the optimizer code again to try to get those two together. I think it's important to characterize the effects of damage in a composite structure. And so it is a good idea to test at various damage diameters or porosity levels and understand what the damage versus undamaged pristine samples look like, because this information could be useful in your designs. A 1/4 inch design allowable, sometimes can actually envelope some of the impact damage events, but not always. For example, a 1/4 inch hole can envelope some amount of damage in this region, but as the damage becomes larger, perhaps you, like this one here, this curve keeps dropping below the 1/4 inch hole design allowable. So it's important when you design a structure that you account for the types of damage you can have in the future, and then perhaps a 1/4 inch allowable may not cover you for everything. Perhaps you want to design to a higher hole size that could cover even this type of impact damage events. So in essence, characterizing your structure to various levels of damage can be extremely helpful in the design of composite structures. And the open hole analysis or testing can help envelope some of the types of damage you may have by characterizing the full spectrum of damages compared to open hole, can help you use the open hole itself to achieve a robust design. Other types of design guidelines, initial design laminates should account for the presence of fastener holes. It could go from 1/4 inch to more. The final design of the composite should provide adequate support for post-impact strength. I've talked about that. So if you have an impact damage event, you should have good residual strength capability to continue to operate. And if not, you want to repair the structure. Having good repair procedures, having good repairs that bring the structure back to the qualified capability of the structure is instrumental and paramount to ensuring that you have a successful structure. Continuing on here, reinforcing plies around the cutout should be interspersed with basic laminate plies. So if you have a region where you have a window or cut, so you want to put a reinforcing plies around the cutout to reduce the stress concentrations from the cutout itself, but then the reinforcing ply should be interspersed with the basic laminate, and that's basically increasing the strength capability altogether. Minimizing the peel stress in thicker stresses, minimizing the peel stresses in thicker regions by tapering the ends is a good idea. Composites, laminates cannot carry significant peel stress, which usually arise due to the moment generated near the end of a bonded joint. And so it's important to then consider tapering the ends. And so that's used as a design solution and to ensure, sometimes they use peel, like basically fasteners to keep the ends, together. And so that's one approach, but in general, you want to minimize the peel stress in thicker joints by tapering the ends towards the free edge, as an example. Balance the membrane stiffness of the adherence, so make sure the membrane stiffness of the adherence is the same on both sides of the joints, and the idea there is to reduce the imbalance so that you can increase the strength as a consequence. Be aware of bonding laminates with significant amount of different CTEs, especially when using high temperature cure adhesives. So that's a similar derivative of the CTE things that we already talked about, but residual strengths present in the joint, residual strengths present in the joint are proportional to the differences in CTE of the adherence and the cure temperature. So it is important to ensure that you can decrease the residual stresses so that you don't, you want to decrease the residual stresses by reducing the mismatch in CTE. We kind of cover that in a different context, but it's the same idea. We also want to use step lap or scarf joints in highly loaded joints. So feel free to pause the video, search these terms and see if you can find them in the literature. But the bottom line is that these type of joints can also minimize peel stresses. And so there are good design practice. Other design practices is to use the most ductile adhesive that can satisfy the environmental requirements. A good design has an adhesive that's ductile. Brittle adhesives will lead usually to low joint strength and greater sensitivity to minor design details. Ensure that adhesive and laminate curing cycles are compatible. If they're not, you can get in a situation where the adhesive cure cycle will be severely degraded and you could have a failure. For example, should the adhesive require cure temperature near the TG of the composite, that adhesive will likely be unacceptable. So it's important to make sure that the materials you're using are compatible for your application. Correct surface preparation of the adherence is essential. Light abrasion of bonded surfaces is necessary. I have a whole lecture on bonded joints in YouTube that I invite you to take a look, and I'll put it in the description of this video at the bottom. But I think it'll be a good 3 hours so adhesive tutorial about this stuff. These are ply drop-offs that I was talking about. Having these ply drop-offs can be very beneficial, but you also want to make sure that the drop-off length, so this length here, be about 10 times to 15 times the thickness. This is not a very good ply stacking sequence in terms of ply drop-off, because it's fairly thick at the length and the thickness are in the same order. You want to kind of decrease that, because otherwise you're going to have this peel effect that's going to pull the composite apart. There's a good design practice where you can apply outer plies to top on top of inner plies, and that can keep everything together successfully. So I recommend you look at that and pay attention to that in your designs. More things are intangible that could get missed. Designers should communicate with manufacturing team. Is the design even doable? Some designs may be challenging to implement in a real life, especially if you're going to be using an optimization code like Hypersizer, or using the codes I discussed in Excel, using Excel. I don't care what design you come up with. It's important to sit down with experienced engineers and ask them their opinion about your design. Does the design make sense? Is it analyzable? Can I simplify my design so we can analyze it in an easier way? Is the design even testable? Those are the questions you want to ask yourself before you start manufacturing your parts and releasing drawings. Please understand the program requirements. We want to make sure that you understand what temperatures, what moisture levels, what factors of safety, what bases allowable you should be using. We discussed A bases and B bases allowable, but every program is going to have very unique considerations. And so you want to make sure that you understand those parameters before you put your design forth. Well, you can put your design forth, but then you have to make sure that you're flexible at modifying those designs to meet the program requirements. It's also important to make sure that the structure is manufacturable. And so we also want to make sure the size, the weight, all that stuff is accounted for, that the materials are compatible with whatever is going to be touching. We don't want galvanic corrosion, for example. So keeping all that in mind is very important. Material selection requires you to do a lot of work as well. Before you just select a material, just make sure that the vendors have enough availability. Make sure that you've done exhaustive research of all the material available from the vendors and select the best one for you. Just because you use composites doesn't mean that everything will be simple. In fact, more likely than not, things will get complicated due to manufacturing errors and many things like that. The vendor could run out of material. You may have to replace the material, and then you're going to have to requal the material, which we discussed extensively. But it's going to take a lot of work, and so you want to be prepared to be able to be robust over the life of the program, that in fact you do have enough material over the long run to really run it smoothly. Now, this is not always the case. Sometimes you just encounter a situation where the vendor may even go out of business. So you cannot control everything, but you can control in ensuring that when you're selecting the materials, they're the best for your application, that they're available, that there's an understanding of what are the propensity of these materials in terms of interlaminar failures and things like that. And I did discuss the Agate database. You guys looked at that, the NCAMP database. There's a whole slew of materials available from the National Aviation Institute research that you can also look at, that's going to help you in making some of these selections. And even if you make the selections of these materials, you want to do some testing in-house to kind of validate your processing, to make sure the material strengths and modulus and all of that are in line to your manufacturing processes. Another thing I want to point out is that it's very important to keep some pocket margin, some additional margin in your pocket. That's why it's called pocket margin for non-conformances. You're going to have manufacturing issues, handling issues. So typically keep some margin, 15%. Some people even keep 50%. I'm not saying go be that extreme, but again, 15% margin, additional margin can be an impact to the weight. So severity penalizes that. but it can also help you with handling manufacturing issues. So you have to basically balance if you really want this much pocket margin, or you have a good sense of how you're gonna incorporate repairs if you were to have non-conformance. So everything here is a balance, right? I'm not going to tell you what to do. All I'm going to tell you is you have to balance the robustness of the design, making sure that you have good repair techniques if you need them, and that perhaps your pocket margins are so sufficient that you don't have to worry about any of that. And so you're good to go. You can use as is. You can use the part as is. I apologize for that. There is a paper that you can find. It's called A Summary and Review of Composite Laminate Design Guidelines, Task 22, NASA Contract NAS 1 19347, published in 1997. There's even better design practices and guidelines available. But here's another point of view from a different set of eyes. Really quickly, almost serves like a summary, but employ balanced and symmetric laminates. Why? It decreases the B matrix, avoids bending, coupling, warping, twisting effects. Avoid stacking too many plies at all one angle. Why? Because the delamination and residual stresses are more likely, if not avoided. Add fabric plies to the inner and outer layer. Why? Because it can help you with impact damage. Add plus minus 45 with at least one pair and laminate at extremes. Why? Because it increases the buckling for thin laminates and also provides you damage tolerance. Use large fractions plus minus plies in shear regions. We already know that from our optimization course, the optimization lecture, and we talked about how shear can be taken very well by these plus minus plies. Plus minus 30, plus minus 45, that's what I'm talking about. 0-90 plus minus 45, we also talked about that. Having one layer of each can be beneficial because it will let you take multi-axial loading conditions and then also provide you an overall stability for the laminate. Now, don't just use your plus minus 45-90 as the only plies, because then you get, of course, a static stacking sequence. And the whole point of using composites is to get creative and be able to exploit how much strength you can get out of them. And so quasi-isotropic is basically black aluminum. You're getting the same properties in every direction. So you may not get the weight savings you were hoping for. A plus minus 45 ply that are in contact with each other can minimize interlaminar stress. And maintaining a homogeneous stacking sequence by banding several plies of the same orientation together can increase strength. And then minimizing the fiber orientation angle between adjacent plies will reduce the free edge effects. And then you can also avoid the micro cracking issues, particularly for high thermal applications. Joint design practices in general. So these are basically looking at joints. I did not discuss this earlier, but I want to bring that to light. For a 0 plus minus 45 90-degree laminate joint, using a minimum 40% plies at plus minus 45 and a minimum 10% plies at 90 degrees is a good idea. It provides overall good strength of the joint by providing good shear out strength, bearing strength, and net tensile strength capabilities. I'm not saying use these numbers, but it's generally a good idea. Maintain a fastener edge distance to hole of 2.5 to 3. So take a hole, the edge distance to hole diameter should be this much, improves the bearing and shear out strength capability. Maintaining a fastener hole spacing to hole diameter of 6.0 is a good idea to minimize the interaction effects between holes. Recall that each hole can cause a stress concentration. If it's too close to another hole, then these two holes will have a stress concentration of their own. And these stress concentrations, their respective stress concentrations will then overlap potentially and then cause a serious issue. Design joints to, try to design them to be bearing critical because they tend to be non-catastrophic. So use fasteners of sufficient diameter, sufficient strength, and locally reinforce as necessary to try to induce a bearing failure and not have a catastrophic failure. Apply all best practices in bonded joints when it comes to surface preparation. Please look at the YouTube video on the bonded joints to learn more about this. But there are techniques to control the bond thickness, for example. For bonded joints, no 90-degree plies in contact with the metal surfaces is a good idea to reduce the potential for the reduction in lap shear strength. Bonded joints of plus minus 45 plies at the very last step in the buildup is a good idea. It reduces the load peaking by decreasing the ply stiffness locally. When adding plies, use a 0.3-inch overlap in major load direction when using a wedge type pattern. And so this is a good idea because it basically increases the strength. Use mechanical joints for direct tensions. Bonded joints do not really develop an adequate strength in that mode, so it's important to really use mechanical joints for those conditions. If you can. Short bonded joints are more efficient than long ones. Many people think that having a long overlap is going to be helpful, but the bottom line is that peak shear stresses will occur at the end of the joints, and that increasing the overlap not necessarily increases the strength dramatically. So there is a bonded joint YouTube video again that you can check out that goes into this. Joint eccentricity produces large peel stresses, so we should avoid them as much as possible. And so there are ways to deal with that. Let me move on to a topic that also has to do with the design of bolted joints. I want to continue this conversation here, and it is connected to the predicting failures, so failure theories. And I'm okay with that covering here because I'm covering what are the design best practices. And so one of the things I want to point out is that when you apply loading to composite, the analytical approach tends to underpredict. It tends to be way conservative compared to the failure load that you may get when you test. And it can be up to 50% lower than the failure load that comes from the testing. Why is that? Typically, because you get some matrix cracking, as we discussed earlier. The matrix cracking acts to reduce the modulus locally, which then reduces the stress concentration, which also means that you may have even a better situation than you originally thought. The linear elastic model from finite elements may not account for that strength, that modulus reduction, due to the progressive failure nature of these microcracks. So let's see how we will predict failure. So here in the y-axis, I have the normal stress distribution in megapascals. In the x-axis, I have the position between from the hole to away from the hole. One of the things I want to point out is when you plot abacus here, the abacus model is this one right here in triangles. There's a closed form solution that will match abacus as well in pink. It follows that. And then using experimental measurements, using some advanced techniques, here's a paper where that came from, stress concentration in a circular hole in a composite plate. What was found is that the open circles here in blue were the measurements from experiments. So they were able to measure stresses near the hole, from the edge and away from the hole. And you can see here how the finite elements matches better at a distance away from the hole. And so using that concept then, what if we don't look at predicting failure right at the edge of the hole, but we look at it from away from the hole where the stresses from abacus and other closed form solutions match those measured from experiments. And perhaps the experiments measure less stress, potentially from these microcracks that reduce the modulus and as a consequence reduce the stress. So experimental measurements show a lower stress concentration really due to the damage occurring near the hole caused by the matrix cracking. If I look at the anisotropic stress concentration factor, the stress concentration factor is defined as the stress here divided by the far field stress. And you're going to see here the EXX bar, EYY bar, all these are the effective mechanical properties you can get for a laminate. And my point here is that this is going to drive the stress concentration factor. You're used to an isotropic material. An isotropic material is going to have a vastly different behavior in general than a composite material. And so here's the formula that was found in one of the papers. This far field stress, that's the far field stress. And then here you get the approximation based on that rho, which is the radius of curvature of the hole. And so I want to point out a few things here, but I want to show you the measured stress concentration compared to the predicted stress concentration for various layups. And this for ball and epoxy. And what you see here is that the stress concentration is consistently higher in many cases for many different ply stacking sequences in general. And that when I start to pressure quasi-isotropic laminate, when I get a 3.0 type, they're more similar. So something to consider here, that when you're approaching quasi-isotropic laminate, things start to change and the analysis starts to match more the measured stress concentration. Very important to consider here, that's not a quasi-isotropic laminate, so therefore you have a higher stress concentration compared to the predicted stress concentration factor. Another thing I want to point out is that when I compare the notch strength versus a pristine configuration, you get a strength ratio of this much. And so this is showing you that you get a significant amount of strength reduction for depending upon the layup that you may have for a plate under uniaxial loading. And so here at the bottom, you have a lower stress concentration factor, but you also have a lower strength ratio from notch strength to unnotched strength. Here you have a huge drop strength ratio because this layup stacking sequence has measured higher stress concentration factor. So the stress concentration factors directly correlate to the finding that the notch strength compared to the unnotched strength can significantly impact the performance of the structures. Another thing I want to point out is the unnotched strength also is impacted by the ply layup as well. So again, all these things are interrelated and should be considered in the analysis or in the design of the bolted joint. So here's an idea that can be discussed. As we discussed here above, the experimental data measured from experiments, these stresses here measured from experiments are in better agreement here with analysis, or the analysis is in better agreement with experiments away from the hole. So let's use that idea and come up with a failure criteria that can be useful in these designs. So what was the idea here? The idea is, let's use the unnotched strength. I have this unnotched strength for this particular laminate, so I'm going to use that data. And what I'm going to do next, I'm going to integrate from this edge to some distance away. Now note how the stress peaks and then drops below this unnotched strength. Very likely at the edge, when you have a notch or a hole, that stress will go above the unnotched strength. But also away from the hole, that stress predicted by Abacus or whatever closed form solution you have will drop below the unnotched strength. So what we're trying to do here is find equal areas here and here that cancel out, or you can find the integral from R to R plus A naught. So basically integrate this stress, okay, from here to some distance, such that when it's averaged over the distance, that I get the unnotched strength. That's the idea. So you have to find A naught to make that happen. One more time, I take the stress integrated from the edge to some distance away. And the idea there is that I'm finding the averaging value that will be equal to the unknown strength. This A naught will be used as a critical distance for predicting failure. Now when I model the hole, I can now predict failure for different kinds of situations. And so here is an example of how the analysis using this approach, it was found the average stress criterion from one test was 5 millimeters. It was found that I was using this approach of the average stress criterion, I was matching testing very well across a whole range of radii. So again, that was done for a particular laminate, but it demonstrates the powerful nature of this approach. Very simple, very, the idea there is that, yes, I have some micro cracking going on. Yes, I have damage going on near the hole, but this average strength criterion is trying to account for that length, that is trying to account for that effect through a length scale parameter, and that length scale parameter here is the average stress criterion, or this distance A naught at which the average value of this stress is equal to the unknown strength. There are two significant amount of literatures that I'd like you to take a look. One is the design of bolted joints, and the BJSFM code. It's a computer program user's manual. Both of these are great reads, so you can see how there are other methods out there that could be used. Now, these are approved for public release and should be able to download fairly easily. The bolted joint BJSFM code is a bolted joint code in Fortran, also available in Excel. The basic idea is that a critical distance is derived from an open hole laminate test, very similarly to the way I did it, where the critical distance is from the edge of the hole to where the failure index is 1. And then the same critical distance is used on a ply-to-ply basis to determine the failure of other laminates with different stacking sequences. This method has been applied successfully in various applications. I'm not going to say that this code is perfect. No code is perfect, but all of them provide you some top-level assessments of bolted joint designs. At the end of the day, you really want to do a test to gain that confidence. I wrote a paper with several co-authors. I did some testing. We did some testing in our labs. And here's the paper I'd like you to download from the 47th AIAA ASME Structural Dynamics Conference in the 2006 timeframe. I'd like you to download this paper, read this paper. What we present there is an approach that's fairly simple, very similar to the approach I just showed you earlier. So it's not that innovative, but it was applied to the prediction of the bearing and bypass loading of a laminate. So what is bearing loading and what is bypass loading? So bypass loading is a loading that's acting far field from the hole, and so that load will go around the hole. The bearing load is the one that the fastener is applying that load into the hole directly. And so the bypass load, if you were to apply bypass load alone with no bearing load, you're likely going to get a net section failure, meaning you're going to crack the composite such as this here on the red that you see there. If you were to apply bearing load alone, you're likely going to cause local damage near the hole, but no catastrophic failure. And so it's important, in this paper, we examine the bearing and bypass load capability of a single loaded and double loaded lap joints bolted designs. One of the things we did in this paper, we used something called the critical area approach, nothing very innovative here, but the idea was to measure the tensile strength of a composite coupon, measure the shear strengths, and then use the open hole testing to come up with that area that will cause failure of these open hole samples. And this area was anchored to these samples and then used in subsequent analysis. And I'll invite you to read this paper to better see how that was applied. And then in that test program, we looked at bypass loading, so that we're only applying the bypass, no bearing load. So in other words, this is a field hole tension because the hole is filled with a pin, but the bypass is really doing the work of applying the load. We also have the double-sided bearing load where you apply a bypass load, but you also apply a bearing load onto the fastener. So you have these two effects combined. And then you have the single-sided bearing load where you have a bypass load and a bearing load only, nothing below. And so when you compare the testing to the model, it's actually very, very close to the test data. All that is shown in this paper. But the bottom, I'm not showing this information to show off. That is not the goal. Is to continue to show that these critical distance approaches or area approaches or similar approaches do have some merit and can be explored. And so with that, I want to kind of conclude the lecture today, and I hope you have a great day.